go ahead and continue our discussion on the pneumatic controllers. So last time I think we had looked at the
Sir, excuse me,
proportional.
sir.
Yes. Yes.
Sir, can you say like which Ogata are you saying, like the control engineering by Ogata?
No, it's not control engineering. Wait, I think, yeah, you are right. There are two Ogata books. One second, let me see the name.
I can find modern control engineering is that.
Yes. This guy, modern control engineering. Correct. So this is modern control engineering. 5th edition is what I have referred. And there's a soft copy available. You can, but as I said, if you understand what I'm discussing in the class, I think just reading the book once will easily help you understand the matter. And the questions will be very similar to what I have discussed in the class. And I think in the midsem also it was like that. But I think the feedback that I get from some of you is the questions are not the same as has been discussed. But if I solve the, questions for you, right, then you will probably realize that everything has been discussed in class. Just that you will need to be a little bit imaginative. It's not going to be a copy paste of what has been what is there in the textbook, right? And similarly, in the anemometer section, or even in the acoustic section that I had discussed before mid-semester, right? There are quite a few things that is not there in the textbook, and it is a little bit different because, as I said, I was not convinced with the approach that the book has taken, and so I went about doing it myself. So here, but for the last few these things, right? It is not. I don't think, other than the optical circuits, right? Optical sensors. There, of course, when I discuss noise, that is my learning from having worked in this domain for so many years. So there will be a little bit of my touch, but these sections, right? I think Ogata has done a pretty decent job, and I didn't see any gaps in deriving in the way he has derived the equations, right? So I think in the last class, right, we had discussed up to this point. I think we had discussed up to proportional controllers, right? Can anybody remind me? I think we stopped here, right, in the last class.
So we have also covered a derivative one.
We covered this one also, right?
Yes.
Okay. Yes. We had also covered this one, correct. So I think we were left with the PI controllers. So if you see here, right, the first thing that you need to kind of realize the moment this kind of a block diagram is given, right, you should be able to realize, which portion is what, in the sense that here, this restriction here is working, it's equivalent to an electrical resistor R, right? And the fact that this is where you give the input signal, and this works almost like a resistor divider. And this can be understood, I had discussed this earlier. This can be understood by looking at, by doing similar triangles. If you see how much this guy moves, then what will be the movement seen here, and how much will be the movement seen here, right? And I had discussed this, by using superposition principle. So the moment you see this kind of a diagram, right, you should be very comfortable in understanding what is what, right? So for example, this guy is my output signal. PC is my output signal, right? So here, what do we see? We see there are two feedbacks, right? So what are the two feedbacks? One, of course, I see is through a resistor, and this below, this is a tank with a capacity C. So this works like a capacitor, right? And so this resistor and this capacitor combined, right, forms one feedback path. So the feedback path will be from here, 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 all the way back here, right? So you should be able to identify that. And then what do we see? If, let's say, PC increases, what happens? The so let's forget about this side. Let's concentrate on what happens to this side. If the pressure increases with some delay, and the reason the delay will be there because of this restriction R that is there. It's like a small nozzle. I don't want to use the word nozzle, but then it's a restrictor R that you see here. This, along with this capacitor, equivalent capacitor C here, right, will tend to move the bellow to this side, right? So what happens is when we increase, when the output pressure is increasing, this guy is moving this side, and what is happening to X? X is increasing. So definitely, this path, there is a positive feedback. If you see here, if you kind of relate to this path here, right? So any movement on PC, if I take the feedback from this path, because the bellow is moving this side, and this node is moving to the left, which means that if this node is moving to the left, that means the effective gap between the nozzle and the flapper here is going to increase, right? So that means it is a positive feedback, right? This loop is a positive feedback. This is understood, right? And if you look at this portion, right, here there is no restrictor. So this is like a pure, there's a direct feedback from here. So if the pressure increases, then this guy moves this side. That means what is going to happen? This guy is going to move this side. And that means the gap, because this node is moving this side, the gap between, so this guy is going to reduce, right? Assume that this is fixed, right? So if this guy is moving this side, not fixed actually. If this guy is moving this side, this is going to move this on the opposite side, and that means this gap is essentially going to reduce. So what you see here is if the output pressure is increasing, there is a proportionality constant. What is this A here? This A is the area of this separation inside the bellow, right? And then there is a Ks. What is the Ks? So Ks you can think of as a spring constant or the bellow constant. So this is Ks, right? So as the pressure increases, depending on the bellow constant, this guy moves outwards, this guy moves this way, and overall what happens is this guy moves in this direction. So the X that you see here, this kind of the gap in this reduces, which is entirely opposite when, so this is entirely opposite when this bellow moves on this side because of the pressure coming from this, because then this guy moves in this direction and this moves in the opposite direction, right? And the X increases, right? So you should be able to quickly, if let's say this question comes in the exam, right, you should be easily able to quickly identify. Again, the question will not be exactly like this. The structure will be a little bit different, but the point is you should be able to identify the structure, and based on the structure, you should be able to come up with this block diagram. And then, of course, you need to be smart enough to do a little bit of mathematical simplification. So, for example, here, instead of having two separate loops, right, what can we do? We can say that, look, here, so this will still maintain as a negative feedback overall. So this part, this portion, I'm representing, I do another adder here, and this guy, I put a negative sign here so that, you know, this negative and this negative, overall it becomes a positive feedback, right? So this guy, I take this portion out here, I take this negative, and then this guy directly goes, because as we see here, this guy directly goes here, and these two are working in opposition, and which is kind of obvious, right? The force working from this side works on this, and whereas the force working because of the increase in pressure will be working in this direction, right? So there is an opposition here. So that's the reason this is minus and plus. So this guy is nothing but what you are seeing here, right? And whatever happens to this guy, this separation here, that force multiplied by the below constant A by Ks, force of course, I mean the pressure multiplied by area divided by the below constant gives the displacement, right? F is equal to Kx, right? So X will be inversely proportional to the constant, spring constant, or the below constant in this case, right? So what happens is this, the total net force working here gets multiplied by A by Ks, right? I mean, A comes because of its pressure. It gets divided by 1 by K, I mean, it gets divided by Ks. And because of that, this node here moves, right? Now, because of the movement in this node, the effective movement here, so this is nothing but like a potential divider, or you can say a scaling factor. This you can look, I've discussed in the previous class. It's also there in the book. It's easy to visualize that if this guy moves on this direction, how much is the effective movement here, right? So this will be A divided by A is this, A divided by A plus B, and then this is fed back. This is a negative feedback, overall negative feedback, and this is my actual input signal that I have here, ES, and this becomes my overall transfer function, the overall block diagram, right? And once I establish this, then it's kind of easy to derive the loop function, right? So then with this, you should be able to quickly derive, and please practice this at home so that maybe at least 1 or 2 examples you should take up, so that you don't struggle with doing this kind of simple algebra. This is not a big deal as such. So here, what you see, right? If the loop gain, so what we mean by loop gain, if loop gain becomes, so loop gain is the overall, so this term is my loop gain, right? A divided by 1 plus A beta. Beta is the feedback factor. So this is my loop gain, right? A beta. So I becomes much greater than 1. I can forget this, right? And what do I end up getting? I end up getting a form like this. And you can again work it out. It's not a big deal, as I said. You can do this simple subtraction here, and then this guy goes on top. And then you should be able to, this PC by ES, PC by error signal. This is a proportionality constant Kp, and you can see B. So this guy stays here, B by A stays here. This K cancels out, A plus B cancels out. This Ks goes on top, right? So this becomes my proportionality constant, and then 1 by TIS becomes my integration coefficient, right? So that means if my error signal, if I give a step input to my error signal, what do I get as my output? The PC, how does it change? It will be a ramp signal, right? So this is an integral of this, and that happens because of this term here, right? And what is the time constant associated with it is RC. So the time constant associated with that is 1 by RC, right? Or RC. The time constant is RC. Any questions on this? Pretty straightforward, not a big deal, nothing, just that you should be able to identify, which component is what, and based on that, you should be able to quickly derive this transfer function. And I mean the block diagram, and from the block diagram you derive this, and eventually you kind of land up with this kind of a simple form, which will tell us that this is a PI controller, right? Okay, so now we will quickly move on to the hydraulic systems, and there also we'll look at the concept of feedback. But before we go there, like quick overview of it. It's widely used in machine tool applications and aircraft control systems. So this is very important for people who will pursue higher studies in controls, right? You will end up, encountering these kind of systems in your academic career in the near future. So the advantages of such systems is high accuracy, flexibility, and reliability. And this again is very important, a high power to weight ratio. This is very important. So the amount of power delivery done by such systems and the weight of these systems, this is so higher is the power to weight ratio, the better kind of controller it is. And this has a distinct advantage over pneumatic, similar pneumatic, systems. Fast response. And then what are the disadvantages? Now, with all these advantages, as we know that there will be some disadvantage, and of course, high cost compared to electric systems. And because the hydraulic systems involve liquids, right? So these are inflammable in nature, and that can cause fire and explosion hazards. And complex dynamics makes it difficult to design a stable system. So this we will see as we discuss in the next few slides. So if you see on the disadvantage side, it's mostly got to do with complexity and cost. So not much in terms of actual engineering care about. Probably this portion is what I can think of as a key engineering care about. Of course, cost is also a part of engineering. But if I take the cost and complexity out, then the only thing that kind of stays as a disadvantage is fire and explosion hazard, right? So the basic structure or the construction of the system needs to take care of this of this issue. Okay, so now let us look at this kind of hydraulic servo system. Servo means again a feedback system, right? There is a feedback which so what this system does is, of course, so there is a liquid, so maybe oil in this tank, and there is a piston here. So there are two pistons, as you can see, one on this side and then the other is on this side here, which actually ends up moving a mass M, a load M, based on the signals that you give here, right? So let's see, what sort of a transfer function we end up with. Please note few things here. PS. So the reason we call it PS, of course, this is pressure, but S kind of denotes this that this is a supply pressure. Okay, and PO here, PO is like it's not the output pressure in this case. In this case, it is, you can say that the pressure here is like ambient pressure, or you can treat this as zero pressure. We'll understand P0. So basically, this is like you can say that it is almost the P0 is much lesser than PS. P0 is like kind of when the system is leaking, let's say, so there is no pressure. P0 we can assume it to be zero, and PS is the supply pressure. And depending on the movement, what we will see is there will be a movement in the fluid in this direction, right? So this is the flow rate. Q is the flow rate. Okay. And the pressure differential across this piston is P1 and P2. Now let's try to derive, the system transfer function on that. So let us zoom in, whatever is here, let us zoom in and see what is going on. So this is my supply pressure PS, and so this is the piston, this guy here, which will be moving based on the input given by the user X, right? So let's say, this guy in the equilibrium condition was right in the center of this channel that we have here, PS. And when X moves either in the left or right, so here in this case, the X is moving to the right, and this dotted structure here gives the placement of the it denotes the new placement of the piston. So what happens because of this movement at equilibrium, let's say, or initially, the piston was right in the center of this channel, and the gap that we had initially was x0 by 2, and this gap was also x0 by 2, half of that, right? Now, because of the movement, because of the signal that we have given here, the piston kind of moves, as I said, and because of that, the opening on this side increases and the opening on this side decreases. And the amount, of course, is x0 by 2 plus x and x0 by 2 minus x, right? So this is this should be understandable from the diagram. And as you can see, the piston by itself has moved a distance x, right? Now we will concentrate, we will focus our attention to these 4 openings that we have. So the orifice areas of ports 1, 2, 3, 4, 1, 2, 3, 4, we are denoting as A1, A2, A3, A4 respectively. And the flow rates through the same ports, we are denoting as Q1, Q2, Q3, Q4 respectively, right? And A1 is equal to A3. From the symmetry of the structure, you have to understand that A1, because the piston is going to move, once the piston moves this direction, all of these guys, these solid structures that you see, they move in the same direction, right? Which means by virtue of the construction, the symmetry in construction, we see A1 and A3 will be same, right? Because these channels, the width of the channel, the construction of these separations, they're all of similar dimensions or exactly the same dimension, right? So A1 will be equal to A3 and A2 will be equal to A4, right? So that means A1 is equal to A3, and we can say that this is whatever K times, K takes care of your, because it's area, right? K times the movement that has happened in the X dimension. This K takes care of your, dimension. K is a, it will have the unit of whatever, meter or inch or whatever, right? So, so A1 is equal to A3 is equal to x02 plus x, and A2 equal to A4 is equal to x02 minus x, of course, multiplied by the same area constant K. Okay. And so this equation, I have alluded to this equation earlier. I had not derived this equation, and I told you to refer. You can refer mentally if you want. So this is an equation that comes from incompressible flow of fluids. I don't think this is discussed either in Ogata. You will not get this equation in Ogata, but the derivation is shown in Bentley. So this is incompressible flow of fluids across a channel with differential pressure across it. So you can read it up if you want. But the point is, the key thing to note is C1 and A1. A1 is the area, and this is the flow rate Q1. C1 is a constant, and this constant has many other things in it. If you are interested, you can look at what are the other things that the C1 is hiding. There is a correction factor, and so this you can say is the discharge coefficient. There are many other constants hidden in this C1, but C1 can be treated as a discharge coefficient. A1 is the area, and that flow rate is proportional to the square root of the pressure differential. So A1, so we are talking of this guy here, right? The Q. So the flow that is happening, the fluid flow that is happening here is proportional to the pressure differential seen at this opening at this point. So if the pressure at this point is P1 and the supply pressure, as we know, is PS, so the amount of fluid flowing in because of the movement of this piston X on this side will be given by C1 times A1 multiplied by square root of. So this actually in Bentley, I think this is derived as the fluid density. So G by gamma, so is actually the fluid density. So gamma is a specific weight. So you will see if you refer Bentley, you will see he writes this as rho here, 1 by rho here, 2 by rho here, but it's one and the same. Ogata writes it in this form. But the key thing here is this portion is the key thing, right? And of course, to remember or to understand that there is an area differential that you have created because of the movement, right? So the flow rate Q1 at the opening here is given by, so as we have seen, A1 is x0 by 2 plus x, right? And this C1, I'm combining, this C1 is a new constant where this K and this C1 and all that stuff kind of is consumed by C1. But again, the focus is on this portion. And by the same logic, by the same argument, Q2, the fluid flow at this point is PS minus P2. Please remember, on both sides, we are assuming that the fluid is flowing into the piston. Here also the fluid is flowing into the piston. On this side also the fluid is flowing into the piston, right? But the fluid flow rate now will be different because the opening at port 1 and port 2, they are now different, right? So the fluid flow rate on port 2 is given by x0 by 2 minus x, right? Similarly, Q3, the fluid flow rate here will be given by exactly the same expression, just that here, so this is Q3, right? So we are talking of this port. And please note, the fluid flow is shown in this direction. It is kind of leaking out of the piston, right? So this is given by, you can say P3, or in this case, P3 and P2 is kind of, we have made it interchangeable. So, and as I had discussed earlier, P0, we will assume it to be 0, that there is no pressure, I mean, there is no fluid pressure at these points. So P0 is assumed to be 0. And based on that, we will say that, Q3 is given by this expression. And Q4, again, the same expression, just that this is x0 by 2 plus x, and whereas this is x0 by 2 minus x. And here on this side we have P2, so this is P2, so this is the same pressure that stays here, P2, right? This pressure is maintained. Please understand that this is the same fluid in the same channel, so whatever is the pressure here, the fluid pressure will be same here, right? So this is P2 on this side, and P1, whatever pressure is here, P1 is on this side, right? Any questions up to this point? Just that we have not shown the derivation of this particular equation, but then we assume that the flow rate will be proportional to the square root of the pressure differential. As long as we understand that, that is good enough, right? So now that we have done this, also let us try to equate based on the flow rate, right? So what is the flow rate on this side? The flow rate on this side is Q1, because the fluid or the oil is entering the piston from this side, and some portion of it is leaking out, right? So the net flow on this side, Q, is given by Q1 minus Q4. Fluid is flowing in from this side, and because of the movement here, and there is no pressure, the P0 is 0, some portion of the fluid is leaking through this orifice outside. So the net fluid flow is given by Q1 minus Q4. And again, by the same logic, the fluid flow that we see on this side is, so what is this this fluid flow here? So this is Q3 minus Q2. So please understand here it is reverse, because this is a fluid that is entering the channel, entering the piston here, and this Q is leaving. So this Q, as shown on this direction, is given by Q3, the amount that is leaving on this side, and the amount of fluid that is entering through Q2. So it's just like KCL, right? Current. It's like just like equating the current flowing through a wire, right? So so this is one flow rate on this side where the fluid is entering the piston, and this is the flow rate on this side where the fluid is actually leaving the piston, right? So, and also, as we know that Q1 will be equal to Q3, because these two these two orifices are kind of same, right? So Q1 is equal to Q3, if you see here, right? So from here, if I equate these two, right? If I equate these two guys, I will come up. Second. So I will say that Q1 is equal to Q3 and Q2 is equal to Q4. And because of this, I can say that PS minus P1. Please look at this, PS minus P1. P1 is the pressure here, is equal to P2. PS minus P1, right, is equal to the pressure P2. Any questions on this?
So can you explain the last one? PS minus P1 equals to
So
P2.
yeah, so this guy has moved. This guy has moved this side, right? So this was which was right in the center. This guy has moved this side, right? So what is the effective pressure seen here? So the effective pressure seen here is PS minus P1, and on this side, I can say that so if you look at so this is P2. So on this side we have P2 here, right? This has moved to this side, and here I can say that the effect of PS, I mean the PS is not kind of taken into consideration on this. I'm just equating the pressure on these two sides. So the effect net pressure, net force that is working on this is PS minus of P1, and this is equal to P2. Is this does this make sense? I will come back to that. I think PS minus P1 is so here the delta P that we see here, right? We'll come back to that point again. But let's say the delta P that we see across this is P1 minus P2. So the delta P that we see on this curve, I mean on this separation here, is P1 minus P2. What I'm doing here, I'm just doing a little bit of a trick. Is I'm referring this P1 as PS plus delta P by 2. And so, one second. So let me go back. So this PS is equal to PS minus P1 is equal to P2. So this is what we kind of left here, right? So the delta P. So can I do, so P1, so what did I say here? So P1 plus P2 is equal to PS, right? So P1 plus P2 if I do, right? These two if I add, P1 plus P2 is PS. Is that clear? So it's like a common mode signal in electrical equivalence, right? So this you can think of as a differential signal, and PS, whatever is the supply pressure here, gets equally, let's say, distributed, half on this side and half on this side, right? So basically on top of a common mode signal, which is the supply signal here, we have a differential pressure built on either side of this piston, right? So with that, if I proceed to look at the flow rate, Q is equal to Q1 minus this flow rate that is flowing in. If I replace, let's go back to the equation probably. The flow rate that we had given here is PS. Q1 was PS minus P1, right? So PS minus P1, if I do PS minus P1 here, I will end up getting this. And similarly, Q4, the same expression. So essentially here, what we are doing is very simple. I go back to this point again. What I go back to this point here is we understand that there is a pressure differential across this, right? And that is the reason it is moving, right? We are moving this, and this movement is creating a pressure differential at this point and this point, right? The pressure on these two sides are not same. So this pressure differential, I am choosing to denote.
Sir? Hello, sir.
Yes, Nayan.
Yes, sir. Sir, how come Q1 equal to Q3 and Q2 equal to Q4?
So Q1 equal to Q3, and so you are saying how come this guy Q1 is equal to, so Q3 and Q2 equal to Q4, right?
Yes, sir. This equation. Like
So,
we are how we were getting this equation.
So let's go back to Q1 equal to, and so this portion, right? This is what you are saying, right? Q1 is equal to Q is equal to Q1. So this is understood, right? Q is equal to Q1 minus Q4.
Yes.
And this is understood, right?
Yes, sir.
So Q1, yeah. So Q1 equal to Q3 and Q2 equal to Q4. So 1 second. So yeah, I'm kind of lost here. I was actually focusing on this, but let's look at. So can I? I'll come back to this, but let's talk about this one. Let's close this first. What Shubham asked. So PS will come to that. So PS, sorry. So PS minus P1 is equal to P2. So the point is, because this guy is moving, we are saying that there is a pressure differential across this, and I choose to denote the pressure differential as the common mode signal. Common mode signal, this supply pressure is common to both sides, right? It's common to both sides. Just that because I have moved, there is still a differential. So I will say the differential pressure is delta P. So because it is moving on this side, I mean, it's moving from left to right, I will say that the pressure on at this point 1 is the common mode signal PS. So P1, I will say half of this guy plus delta P. Half. So basically PS plus delta P divided by 2 is on this portion, and PS minus delta P divided by 2 is on this portion. This is how I choose to denote without losing any generality, right? So is that okay, Shubham?
Yes, sir. Yes, sir. Got it.
Okay. So now let's look at Q1 equal to, yeah, this portion. I'm just kind of lost. So 1 second, let me just recollect. Q1 equal to Q3 and Q2. So we are saying Q1 is equal to Q3. The amount that is entering, yeah, and Q2. So Q1 is the amount that is entering, the amount of fluid that is entering on this side, right? So this is Q1, and the amount that is leaving is Q3 on this side, right? And similarly Q2, so the amount that is leaving, yeah, I think so this is the flow rate. So essentially, let's look at the expression here. Q1 is, we are saying Q1 is equal to Q3, right? And Q1 we are saying is PS minus P1. I'm kind of lost here, Nayan. Can I get back to you on this next class? I'm kind of lost here from where I think this is probably for, is it for the steady state condition?
Sir, if we look at the expression like POS minus P1, if we replace it with P2, then the both expressions are same.
Repeat, please. PS minus P1
is P2, which we just discussed.
Yes, PS, yeah, that is one way to, PS minus P1 is equal to P2. Yeah, that is true, but then, yeah, so basically, yeah, correct. In fact, if you see, so one from a dimension point of view, Q1, this dimension and this dimension matches, right? Q1 and 3, this matches, right? That we talked about. And Q4 and Q2, the dimension matches, right? So the area dimension matches here, and PS minus P1, yeah, is equated with P2 here. Yeah. That, yeah, yes. that can be one way to explain. But I think I was trying to think of more of a physical explanation. Nayan, you wanted to say something?
So I wanted, let's say that Q1 equal to Q3 and Q2 equal to Q4. That animation came before PS minus P1 equal to P2. So I thought like if we are assuming Q1 equal to Q3 and Q2 equal to Q4, then equating those equations Q1 equal to Q3, we can get PS minus P1 equal to P2. I thought like that, but
No, no, correct. That is the right thought process, and that is the reason I was trying to get a physical
yeah,
explanation for this.
yeah.
Your point is valid. The point is valid actually. So no, so this, for example, is more of a, so even on this side, we can easily challenge if we see, right. This guy has moved. So see, this is what we have zoomed in, right. So the pressure at this point is what we are seeing is PS minus P1, and here it is P2, right? But then, we are kind of saying that because this guy has moved, the pressure in at this point, right? So what is this pressure, right? So Q2, when we write Q2, right? Here we are writing PS minus P2, right? Here we are writing PS minus P2, right? But then when you are equating on this side, we are saying that PS minus P1, PS minus P1 is equal to P2. Now here, I'll get back to you on this. Actually, I'll get back to you on this. This I think I had thought about this, just that I'm not able to recollect. I'll get back to you on this, right?
Okay.
So yeah, so let's proceed. I'll tomorrow, once we reconnect, I will get back to you on this which comes. So Nayan's observation is correct. What he's saying is, first we said this, and that is correct. First we said this, and based on this only I think it has got to do with some sort of conservation. We'll come to this, but for now, let us proceed with the mathematics. But this is very important, the way, and this is a technique that we use for electrical signals also. Whenever we represent electrical signals, right, we break it down into common mode and differential signals. So this is exactly the same stuff that we have done in equating the pressure here. So this I think is understandable. And Q, the net flow rate, this I think is also pretty understandable, is Q1 minus Q4, the fluid entering through this and the fluid exiting through this channel. Will be given by, again, the incompressible fluid flow equation that we saw. So this, we are just replacing the area term as x02 by x0 by 2 plus x and x0 by 2 minus x, right? And this is the pressure differential that we have kind of written. Now, important thing to note is this flow rate. We can say, so what do we make of this big equation, right? It's kind of seems to be a large equation, right? So this is safe to say that the flow rate is a function of two things. It's a function of x. X0 is of course constant. PS is constant. So what, C1 and C2, these are constants, right? So it's safe to say that the flow rate is a function of x and delta P, right? This is understood, right? So if this is the case, I can write, so Q bar is, let's say, so essentially it's like this, right? We have, it's like a three-dimensional thing. So you have Q on, let's say, the z-axis. On the x-axis, let's say we have x, and here we have delta P. So it's like a kind of a curve on a three-dimensional plane, right? On a three-dimensional, it's a 3D curve, right? So there, how can we represent so small changes around an operating point? So this, can somebody say what is this kind of an equation? This comes from Taylor series, right? If you look at what Taylor series says, that around an operating point, if I take incremental, if I increase Q slightly, actually this is my dependent variable. So I should say if I increase X slightly from the operating point, and if I increase or change, I should not say increase, if I change X around the operating point x bar, and if I change the pressure around the operating point delta p bar, this A and B, these are nothing but slopes, assuming that the higher order slopes are negligible, higher order differentials are negligible, right? So these can be around, if everything is very small, incrementally small, A is given by del f, whatever this function we have, del f del x, keeping x equal to x bar and del p equal to del. So around that operating point, if I do a differential slope calculation with respect to x of this function f, I come up with a coefficient a, and similarly I come up with a coefficient b when I do del f by del p. So this is nothing but my Taylor series expansion. So the book doesn't mention that this is Taylor series, but this is exact. So this is pure Taylor series approximation, neglecting the higher order terms, right? So you can find the slope a and b of the of this function that we have, and this will be given in this format, and of course b will be given as this. Again, that is not so much interesting. The maths here is not so much interesting as the equation in itself here. This I think we can just find. So a and b are called the valve coefficients, and at normal operating point we will know that we of course know that x bar will be 0 at normal operating point. This will be 0, and del p also will be 0, and the average flow here, the flow in the normal operating point, the flow will be 0. There will be nothing when there is no movement, right, in the system. The average will be, all these averages will be 0, right? So once we make these guys 0, I can write Q, the incremental flow rate, as a function of x and delta p. That I can write, right? And K1 is of course, this given by, so once you write Q as a function of, you take these guys to be 0, so then K1x, so K1 x is nothing but, if you see here, right, delta p is 0, so we take C1, so Ts by 2, so this guy, we take this guy common, and C1 plus C2, so K1 comes from A and K2 comes from B. Just that in B we have just replaced x bar as 0 and del p bar. The average pressure difference is 0, right? So A gives me K1 and B gives me K2, right? So with this, I can come up with a flow equation here, which will be given as K1x by K2 delta P. So today we will stop here and we'll revisit, we'll look at this portion again tomorrow, just to ensure that the only gap that we have here is in understanding from where we got this. If we get this portion, then these are all understandable. These are all understandable, right? So we'll look at this portion tomorrow, and then we'll continue deriving the servo system. But as I said, the key thing once you read the book also is to understand, or to be able to identify the block how to go about constructing the block diagram, and from there how to derive. Once you have the block diagram, everything else kind of falls in place. You can derive the transfer function, and from the transfer function you can look at the system characteristics, right? Whether it's an integrator or a differentiator or a just a simple proportional system that you can figure out, right? Okay, so we'll stop here for today, and then tomorrow we'll continue. Yeah, thank you.